This is part 2 of the lecture covering kinematics and definitions. At the end of part 1, I illustrated the difference between average speed and average velocity. I also described how those average quantities are easy to calculate, but they don't tell us what's important. They don't tell us, for example, what happens with an object at an instant in time, such as, for example, as would be necessary in describing the motion of a projectile. So then, therefore, if the average quantities are not very useful, what is it that they actually tell us? Well, they lead us to the following description. What I'm going to do is I'm going to construct here a simple graph, the hypothetical graph of the position of an object as a function of time. All right, so time here is going to be on the horizontal axis, and then position here on the vertical axis. Then as an object moves along a number line, let's say that the function that gets traced out, whatever it may be, is some sort of smooth curve polynomial, just for simplicity. For example, that would say, look, something like this. Like so. And then we take a look at two instants in time. Let's say at this point right here, where we start the clock, and at this point right here, where we stop the clock. This then means that along the time axis, this distance here, if you will, is equal to the time interval delta t. And then right here when we start the clock, the object has here on the position axis an initial position x naught. Right here after we stop the clock, the object has a final position x like so on the position axis. The difference between the two is the final position minus the initial position. It's the change in position delta x. Okay, now I'm going to use a ruler to connect these 2 points here such that I form a line. This line is given a couple of different names. It's referred to as a chord. It is also sometimes called a secant line, and is drawn like so. Like this, intersecting my red polynomial here at these 2 points. And now let me go ahead and calculate the slope of this line. Slope, if you recall from mathematics class, is rise over run. The rise is the change in position, delta x, and the run is the change in time, delta t. Notice what it is that I'm calculating here. Change in position divided by change in time is average velocity. As we've seen, however, the average velocity is easy to calculate, but it doesn't tell us what happens at an instant in time. How do I then go to that description? Well, what I have to do here on this graph is take this time interval, delta t, and literally make it infinitesimally small, such that it has 0 size. On this graph, this then looks like this. Okay, so I'm going to go ahead and construct here the same polynomial. So position as a function of time, this red polynomial like so. And now let's say we want to know exactly what is happening right here at this instant in time. Exactly how is this red polynomial describing position changing right here at this instant in time? Well, it's once again going to be the slope of a line. But in this case, it's the slope of a line that is tangent to the curve. In other words, it only intersects the curve locally at that point. That looks like this. Like so. The slope of this green line, what is referred to as the tangent line, describes exactly how the position is changing at this instant in time. This is referred to as instantaneous velocity. Instantaneous velocity is just referred to as v. It's the same thing as the average velocity, but now what we're doing is we're taking the time interval delta t from this graph and we're making it literally infinitesimally small, literally of 0 size. How do you then take something, the change in position, and divide it by 0? That mathematical position, or that mathematical question, flummoxed mathematicians for more than 2,000 years. The ancient Greeks tried to formulate a description of motion. In order to do so, however, it literally involves taking quantities and dividing it by 0. That particular problem was solved more or less simultaneously in the 17th century by two people, Isaac Newton in England and Gottfried von Leibniz in Germany. This is the basis of what is called differential calculus. Position, if you take the derivative of it with respect to time, is velocity. The derivative of position with respect to time is the slope of this green line that is tangent to the curve. Instantaneous speed is the magnitude of the instantaneous velocity vector. Here's how you can keep the two straight. For example, let's say that you're sitting in a car going down the freeway at 60 miles per hour, and you look at the speedometer. You look at the speedometer. The speedometer is giving you your instantaneous speed, 60 miles per hour. But let's say that you're traveling to the north. Therefore, your instantaneous velocity vector is 60 miles per hour to the north. There's a magnitude, 60 miles per hour, and a direction associated with that vector. So as position changes with respect to time, that then leads us to velocity. Velocity, however, could also change with respect to time. That's what's called acceleration. Let me describe first of all the average value, and then I'll once again go through a process like this that describes the instantaneous value. Let me erase first. Okay, first of all, average acceleration is written as A, and then we once again use a bar symbol for average. By definition, average acceleration is change in velocity with respect to time. Let's take a look at the notation associated with the numerator of this expression, change in velocity delta V. Change is always final minus initial. So the final value of the velocity is referred to as V, and the initial value is referred to as V naught. Once again, there's a little bit of tail-to-tip method of vector addition that is present here in this expression. In order to see the tail-to-tip method of vector addition, I'll do an extra step by taking the initial velocity V naught and moving it to the other side of the expression. When I do, that then gives us the following. So initial plus change is equal to final. Let's illustrate how this works with an example. Go ahead and copy down the next example in your notes. I have to put it here up onto my screen in order for me to go through the solution. Okay, let me read to you the problem. A bicyclist is moving at positive 5 meters per second. The plus sign indicates that the initial velocity vector is pointing to the right-hand side. The magnitude, the initial speed, is 5 meters per second. 30 seconds later, the bicyclist is moving at negative 10 meters per second. The negative sign means that the bicyclist is moving to the left. What is the change in velocity? And then what is the average acceleration? Okay, so in the example, we now have the following quantities. First of all, the initial velocity V naught. That's positive 5 meters per second. The final velocity V, that's negative 10 meters per second. So then therefore in part A of the problem, we could immediately calculate the change in velocity, final minus initial. So negative 10 minus 5 is negative 15 meters per second. And then on a number line representing velocity, not position, but on a number line representing velocity, we can now show the tail-to-tip method of vector addition using this expression here. All right, so here's a number line representing velocity in terms of meters per second. Say 5, 10 to the right-hand side, 5, 10 to the left, like so. And then in order to show the tail-to-tip method of vector addition, we begin with the initial velocity v naught, that's positive 5 meters per second. That then looks like this. And then we add to that then the change in velocity vector delta v. That's negative 15 meters per second. So I'll put the tail then of delta v at the tip of v naught. That then looks like this. Okay, once again, however, I'll go ahead and draw it below the number line such that you can easily see it. And then therefore the resultant, the final velocity v of negative 10 meters per second, that then goes from the origin where I started this process to then 10 meters per second to the left-hand side. So then here's how you pantomime the tail-to-tip method of vector addition with this expression. We have the initial plus the change, that then equals the final, like so. Okay, now, secondly, in part B of the problem, we go ahead and calculate the average acceleration. Change in velocity divided by change in time. So negative 15 meters per second, and then divided by the change in time, which is given as 30 seconds. Now 15 divided by 30 is just a half, so this is negative 0.5, and then we once again take a look at the units. Do the seconds here cancel? No, they multiply together. We write this as meters per second squared. Here's how you can easily see how the units work. In the numerator of the expression, we have meters per second, and then we're dividing by seconds, which is the same thing as multiplying by 1 over seconds. So notice that the second symbols here multiply together to then give you seconds squared in the denominator of the expression. Therefore, the units are meters per second squared. Acceleration is a vector quantity. It's a vector quantity because the numerator of the expression is a vector quantity, the change in velocity. So then therefore, on its own number line, I could represent the average acceleration vector. I can't represent it on this number line here because this number line represents velocity. Instead, acceleration has to have its own number line. That looks like this. So now this is representing acceleration in terms of meters per second squared, and then I have here 0.5 to the left-hand side. So the average acceleration vector for this problem, A bar, looks like this on its own number line. Incidentally, by the way, drawing these number lines over and over for the individual vectors is considered somewhat redundant. From this point going forwards, I won't bother to do so. We'll just go ahead and draw the individual vectors themselves, and that's perfectly fine. Now in this problem, calculating the average acceleration, as you saw, was easy to do. It's just a little bit of algebraic manipulation. But once again, it's not a complete description of motion, because in order to describe motion, you need to know what is happening, for example, at an instant in time. So then here's how we arrive at a description of instantaneous acceleration. Let me go ahead and erase the board to illustrate. Okay, now as an object moves along a number line, let's say that in this case what we graph out as a function of time is velocity. And once again, for simplicity, let's assume that it's some sort of smooth curve polynomial that gets traced out like so. And then we take a look here now at 2 moments in time. So for example, right here, let's say that's when we start our clock. Right here is when we stop our clock. So then therefore, this distance here along the time axis is the time interval delta t. When we start the clock, however, here on the velocity axis, we have an initial velocity v naught. When we stop the clock, right over here, we have a final velocity v. So notice that this distance right here on the velocity axis is the change in velocity delta v. And now I'll once again go ahead and connect the 2 points with a chord, a line, and then let's calculate the slope of that line. All right, so connecting those 2 points like so. This green line here intersects the red curve here and here, and then we go ahead and calculate the slope as rise over run. The rise is the change in velocity delta v, and the run is the change in time delta t. Therefore, the slope of this line is equal to the average acceleration. In order to describe, however, what happens at an instant in time, we have to, once again, take this time interval and literally make it infinitesimally small. That then changes the graph such that it looks like this. Okay, so once again, we graph out here velocity as a function of time. Right here is our curve. And then let's say that we're interested in knowing exactly how this red polynomial is changing right here at this instant. If I know exactly how the velocity is changing at that instant, I then have a description of the instantaneous acceleration. We're once again calculating the slope of a line, but in this case it's a line that is tangent to the curve. It only intersects the curve at that point. That looks like this. Like so. The slope of this green line here indicates to us exactly how the red velocity is changing right here at this instant. The slope of that line is then therefore the instantaneous acceleration. The instantaneous acceleration is simply written as A. It's exactly equal to, once again, this quantity here, but we now take the time interval and make it infinitesimally small. This is another derivative. Acceleration is the derivative of velocity with respect to time. In order to calculate it, strictly speaking, it involves taking the quantity and dividing it by 0. Differential calculus is necessary to do that. What I have done here in these 2 lectures is all that I have done is I have defined things: position, velocity, and acceleration. Velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. You begin to understand more and more exactly what is meant by position, velocity, and acceleration by using these definitions. That's what we do throughout the remainder of this unit on kinematics, thereby leading to an understanding of the mathematical description of motion.